Hello everyone, my name is Ryan Chen and my partner's name is Net, and today we'll be talking about how to use a Michelson interferometer for nanoscale surface metrology. And this topic basically means how do we measure nanoscale objects at a very precise measurement. So first we'll introduce the topic and introduce what we have learned in class, and then we'll explain the Michelson interferometer, and after that we'll explain 4 necessary components for nanoscale profiling. And finally, we'll show you a real-life lab experiment that we did and show you the lab results. So starting from the most basic and fundamental phenomenon in classical optics, interference, which serves as a foundation for the Michelson interferometer, which we'll talk about later. And this equation right here is the basic interference equation that shows that when 2 light waves combine, their intensity, which is denoted by I, is a function of I1, I2, and phi. I1, I2 being the intensity or brightness we see at I1 and I2, and then phase difference between the 2 beams is denoted as I. And this equation comes from the superposition of electric fields, and as you will see later on, our topics heavily based on this phenomenon. So next we will talk about the Michelson interferometer, which was invented by Albert A. Michelson back in 1881. And this optical instrument splits a beam of light, which in this case is laser, through a beam splitter, and it goes into 2 different paths, that is at a 90-degree angle. And at the end of the paths is a mirror that reflects the beams back. And the beams meet back at this beam splitter and creates an interference that we can observe on the screen. A fun fact is that in Washington State, in the United States, at a military site called Hanford, which used to produce plutonium that was used in the first nuclear weapons, also houses a giant Michelson interferometer. And this building contains a beam splitter and a laser, which is split into 2 paths down this 4-kilometer pipe. This is a bigger scale, as you can see, and at the end of the pipe is a mirror that reflects it back, so exactly like how this diagram shows. And back at this building you can observe the interference patterns. This giant interferometer is used to detect gravitational waves. So the core idea of this is that depending on the path difference, they interfere constructively or destructively, and we can use the interference patterns to reveal the optical path difference, or the OPD. And from that pattern, you can measure tiny distances, wavelength changes, or refractive indexes, or in this case, surface profiles with extremely high precision, down to the nanometers. So now we'll get into our topic, which is nanometer surface profiling with the Michelson interferometer, and basically refers to measuring surface height variations with vertical resolution on an order of nanometers. And this is useful because it's essential in semiconductor manufacturing, thin film inspection, optical component testing, and a lot more. So the first necessary component of this is the phase shifting interferometry, also known as PSI. And what this is basically a technique that takes multiple pictures of an interference pattern while the phase is slightly changed each time. And the phases are 0, 90, and 180, and 270. As you can see right here, it's 0, pi over 2, pi, and 3 pi over 2. And because the brightness of the fringes depend on the phase difference, as we can see right here, changing the phase in a controlled way lets us figure out exact phase value at every point in the image. And after this derivation, we end up with this equation right here, which has an inverse tangent in terms of I1, I2, I3, and 4. Next, we move on to the spatial light modulator, or the SLM, which is what we use to create a phase shift in one of the beams. So basically what we talked about in the last slide, how we implement this phase shift is by using an SLM. So in simpler words, they act like digital mirror whose surface can be changed electronically by sending them different gray level values. So as we can see right here, this is the SLM. After observing the interference patterns and the phase, calculating the phase, we see that it's an arctangent, an inverse tangent right here, and in terms of I1, I2, I3, I4. And what that implies is that it's restricted on a scale at negative pi and pi. So it's restricted between these. So to recover the physical phase, we must use a process called unwrapping. And this usually is carried out by an algorithm that examines the neighboring pixels and corrects the jumps that happens to reconstruct a smooth phase map. So as we can see right here, it goes down and ignores the jump, goes down even more, ignores this jump, and then completes this graph. And on the right, we also see this example of wrapped and unwrapped phase. So once the wrapped phase map is obtained from the phase shifting algorithm and unwrapped to produce a continuous phase distribution, as we explained earlier on, the surface height profiles can finally be calculated using the optical path relationship of the Michelson interferometer. And if we denote a height variation of h on the sample, it introduces an OPD of 2h. This is because the beam travels down the path to the surface and back. And this optical path difference produces a phase shift of 2 pi over lambda times the OPD. And this implies that we can find the physical height difference if we have the phase. So lastly, I'll show you a real-life experiment that we did. This picture was from an event that I took a picture of, and this shows the setup of the Michelson interferometer that was used for nanoscale profiling. And this machine, this little thing right here, is the SLM. As you can see, this is a Michelson interferometer setup. And basically, to do nanoscale profiling, we have to align a Michelson interferometer and then configure the SLM and calibrate, and then record the different phase shifts, and as we explained before, find the wrapped and unwrapped phase maps, and then convert it to the physical height map. So this is the actual interference that we captured, and we captured a lot more than this, but these pictures are sent into a Python program that analyzes this picture for us. And as we will see later on, these are the results. And this is the first graph right here is the wrapped phase. And we'll use a sample as shown over here that is kind of like a cross, but this is not the exact sample we use. But it's about the same. So as you can see, there's a tiny, you can sort of see the cross over here. And then with this, we can pick a line that we want to analyze and then graph out the wrapped, unwrapped, and final phase according to this. And after that, we have the wrapped and unwrapped phase. We can convert it into height, and then what we have right here is the height map. And so you can sort of see the cross becoming a bit more easy to see, and this scale is down to the nanometers. So our conclusion is that to use a Michelson interferometer to measure nanometer objects, we introduce different phases with an SLM, record data and plot it on the graph, which would be a wrapped phase. And using different algorithms, we unwrap the phase to obtain the unwrapped phase. And then lastly, we convert it into the final phase into height. So that would be the height map. And here are our references. And thank you for watching.